Thanks for the introduction. So in this talk, I'll discuss some results in meta-learning and self-play, which are topics which are fairly interesting. So I'll begin with a slightly higher level introduction by telling you about the reinforcement learning problem. The reinforcement learning framework just tells you that you have an agent in some environment and you want to find a policy for this agent that will maximize its reward. And it's a super general framework because almost any problem you can think of can be described as there is an agent which takes some actions and you want to take those actions which lead to the good rewards, the high rewards. Now, the reason that reinforcement learning is interesting is because there exist reasonably good reinforcement learning algorithms. I shouldn't say reasonably good, I should say interesting reinforcement learning algorithms that can sometimes solve problems. So in the formulation, the environment gives the agent the observations and the rewards. But in the real world, the agent needs to figure out its own rewards from the observation. Humans and animals, they're not being told by the world that something is good or bad. It's on us to figure it out for ourselves. And this is how it looks like. You got a little neural network. Sorry, this is how it looks like right now, at least, where the observations come in and a little neural network, or hopefully a big neural network, does some processing and produces an action. And I'll explain to you in this slide the way in which the vast majority of reinforcement learning algorithms work. It's these 2 bullet points. You try something random, and if you did better than expected, do it again. And then there is some math around it, but that's basically the core of it. And then everything else is like slightly clever ways of making better use of this randomness. Okay, so now I'll dive into, oh yes, important slide, the potential of RL. Why is RL cool, really? The reinforcement learning algorithms that we have right now, they can solve some problems, but there's also a lot of things they can't solve. If you had a super good reinforcement learning algorithm, then you could build a system that could achieve super complicated goals really quickly, and basically the technical portion of the field of AI would be complete. And a really good algorithm would combine all the spectrum of ideas from machine learning, both supervised learning and unsupervised and representation learning and reasoning and inference at test time and training at test time. All those ideas would be put together in the right way to create a system which would figure out how the world works and then achieve its goals in this world and do it really quickly. But the algorithms we have today are still nowhere near at the level of what they can be in the future and will be. So now let's discuss some ways in which we can improve reinforcement learning algorithms. And I'll describe to you one very simple improvement. The improvement boils down to this. It's a really simple idea. So as discussed earlier, the way reinforcement learning algorithms work is that you try something random, and if you succeed, if you do better than expected, then you should do it again. But what happens when you try lots of random things and nothing works? This is the case when exploration is hard, when your rewards are infrequent. You get a lot of failures, don't have a lot of successes. So the question is, can we somehow find a way to learn from failure? And I'll explain to you the idea very briefly. The idea is the following. You try to do one thing. You aim to achieve one thing. But you will probably fail unless you're really good, so you'll achieve something else. So why not use the failure to achieve the one thing as training data to achieve the other thing? It's really intuitive and it works. And I'll show you a video. I'll show you a video that explains the algorithm and also shows some cool results of what it can do. So let's see, let's jump to the more interesting part. Yeah, so you see you can train this robot, simulated robot hand to move the cube in lots of different desired configurations. So these are trained policies. And it kind of looks cool. This hand is really, it's just fun to watch. And you can apply, of course, you can apply this approach to many different settings. What you need is you need to have some kind of a parameterization of goals, so that every time you try to achieve one goal, if you fail, you may achieve a different goal. Okay, now there's going to be a cool explanation of the algorithm, so I'm going to jump to it. Okay, there you go. So basically, I don't even need to say anything because it will become clear. So you got your robot, it tries to achieve the goal, but it failed. Instead, it achieved something else. It achieved an outcome. And we'll just treat this outcome as the goal we intended all along. And there you go. Now you're learning from experience. So, failure has been turned to success. Okay, great. Now we know how to turn failure to success. Let us move to the next method I want to describe to you. So there is this, one of the areas of research we work on is robotics. And the reason for that is that robotics gives you all these cool problems. It makes you grapple with reality. And the constraints that the robot imposes on you are good constraints that you'd like your algorithm to be able to meet. And one of the things that would be very nice when it comes to dealing with robots is if you could somehow train a system in simulation and then take its knowledge outside of the simulation onto the real robot. And here, I'm going to show to you a really simple way of doing that. Let's see. The idea is the following. You know that there's going to be some difference between the physics of the simulation and the physics of the real robot. And what's more, this difference can be hard to pinpoint. Because can you really determine what are the very subtle differences? Well, maybe you actually can. But it would definitely take a lot of work. So I don't want to say you can't do it. That's probably false. But something which you can do to help your policy is to randomize many dimensions of the simulation. So you could randomize gravity, friction, torques, lots of things. So now when you place your policy into the world, it doesn't know what are these different dimensions that you've randomized. It needs to figure it out on the fly. So it's a recurrent neural network, and as it interacts with the environment, it figures out how the world really is. And it basically works, or at least it works in some cases in an interesting way, and I'll show you with the video. Actually, you can see the video already, it's playing. So here, you train a policy in simulation without the randomization, and you're trying to bring the hockey puck to its goal, to the red dot, and it's not succeeding. It's confused. It's shaking because the world behaves in a way that it doesn't expect. Now, if you train with these different randomizations, then the neural network, the recurrent neural network, is able to, in effect, try to do system ID and try to guess all the unknown little coefficients that it's already learned to identify just from the observations. So you can see that it's very clearly closed loop. Look at this. So that's cool. So there you go. There is a very simple way of doing Sim2 Real, and it might even scale to more difficult setups. I'll also show you two more simple works. This one right here by Franz et al. Is a simple approach for learning a hierarchy of actions. So one of the things that would be nice to do in reinforcement learning is to learn with a hierarchy of some kind. But it's never really been successful, truly successful. And I don't want to claim that this is a success as well. This is more of a demonstration of how you could approach the problem of learning a hierarchy if you had a distribution over tasks. If you have a distribution over tasks, then basically what you want is to train low-level controllers such that they make it possible to solve the tasks quickly. So you optimize the low-level actions such that they make it possible to solve the tasks from your distribution of tasks quickly. And that approach basically works on this domain where you have this little ant crawling around, and it learned 3 sub-policies. So this kind of big problem was quite easy to learn because credit assignment is easy and so on. Like hierarchical RL is still unsolved. This is not the solution, but it's an interesting demonstration that perhaps will lead to this solution. I also want to show this cool result, where basically we thought, OK, it would be kind of cool if we could evolve a cost function which could make it possible to solve RL problems quickly. And as you usually do in these kind of situations, you have a distribution over tasks, and you literally evolve the cost function. And the fitness of the cost function is the speed in which this cost function lets you solve problems from a distribution of problems. And I'll just show you. So this is a single, is it playing? Let's see. Go. OK, great. Really? Yeah. So this is going to be a slightly long video of a single learning trial. Once the cost function has been learned, then learning is extremely fast. This is also a continual learning trial. So it's constantly updating its parameters, and it's trying to achieve this green half sphere. It's a little jittery, but after a while, it will succeed. So the learned cost function allows for extremely rapid learning, but the learned cost function also has a lot of information about the distribution of tasks. So in this case, this result is not magic, because you need your training task distribution to be equal to the test task distribution. And now it's improved some more. And basically, it will improve, and in like 2 minutes, it will be really good. But it's because the cost function is really, really good for this. And then we've also been able to show some generalization where the cost function has never, ever been shown, taught how to move to the left. It's only moved to learn to the right. It's only moved to walk. Sorry, the cost function has only ever been trained to move to the right. And so it figured out how to, in effect, walk in a circle. So it's, again, this is a super fast learning trial, and it's kind of cool. All right, next topic. We only have 2 topics to go. Self-play. So self-play is something which is really interesting. It's mysterious. It's an old idea that's existed for many years, back from the 60s. The first really cool result in self-play, the truly cool result, is from 1992 by Jerry DeSauro, where he used a cluster of 386 computers to train a neural network using Q-learning to play backgammon with self-play. And the neural network learned to defeat the world champion, and it discovered strategies that backgammon experts weren't aware of, and they agreed that those strategies are superior. So it's a super modern paper, except that it's written in 1992. And if you look at this plot right here, which shows the performance of the different neural networks, you've got the number of hidden units and its performance. And you see that as you have the most incredible pattern, by the way, that more hidden units result in better performance. And this could have been a 2018 paper or 2017 paper if you had a couple more zeros right here. But I find this work to be so amazing because it's been so long ago. and yet it's been actually successful. It got the result. And in many ways, very little has changed. That's not entirely true. It's a little bit unfair, but on some level, very little has changed. And then we've also heard of the AlphaGo 0 result, which was able to beat all humans in Go from pure self-play. So self-play is beginning to work. There is also the our result on the Dota 2 1v1 bot, which was also trained with self-play, and it was also able to beat the world champion in 1v1. So self-play is beginning to work. But what is exciting about self-play? So self-play has the property that you can have very simple environments, yet if you run self-play in a very simple environment, then you can potentially get behaviors with unbounded complexity. Self-play gives you a way of converting compute into data, which is great because data is really hard to get, but compute is easier to get. Another very nice thing about self-play is that it has an extremely I can't think of the word, maybe balanced, maybe natural. It has a very natural curriculum because if you're good, then your opponent is good. So it's always difficult. You always win 50% of the time. If your opponent is really good and you're really good, it's still difficult. So it doesn't matter how good you are or how bad you are or not the bot is or the system is. It's always challenging at the right level of challenge. And so it means that you have a very smooth path of going from agents that don't do much to agents that potentially do a lot of things. So this is why I find the idea of self-play exciting and appealing and worth thinking about. And people have. In the past, there's been work by Carl Sims from 1994, where he's already tried to evolve artificial life. In this case, they were competing for a little green cube. And he's been evolving their morphologies as well as their policies. And that's nice. And one thing that we tried to do last summer was to see if we can use self-play in a physical environment. So the hope here was basically to evolve a martial art. And we kind of did, except that these humanoids, they don't feel pain and they don't get tired. So their martial art may be a little different from the ones we would get. But the cool thing about this is that no supervised learning was used. This is basically creativity. You simply say, hey, here's an environment. Can you please figure out what to do here? And they discover something which I think is a legitimate martial art. Here's another one. And so the reason these are so interesting is because I'll let them play soccer a little bit more. So they produce policies that are, okay, look at this. That was a nice dodge. Oh yeah, so this one is interesting. So this is transfer learning. You take one of the sumo wrestlers, and you take its friend away. So now it's standing in the ring friendless. And you apply big random forces on it. And as you can see, it is able to do a decent job at maintaining its balance. And the reason for that is that it's already used to someone pushing on it. And that's why it's stable. And so one thing which I was hoping we would be able to get out of it is something like you put these robots in self-play, and then they learn all these physical skills, and then you can fine-tune them to solve some useful task. So this is something which hasn't been done yet. The closing the loop of taking an agent outside of the self-play environment and maybe fine-tuning it on some task which we otherwise cannot solve at all. Now, I want to say one last thing about self-play, and this is more speculative. Can such self-play system lead us all the way from where we are right now to AGI? And one useful thing to do is to look at biological evolution here. We know so there exists at least one science paper that claims that social species are more intelligent. And you can kind of see why, because they have all these other agents they have to contend with. And so I used to be very convinced that this is what's going on. But then I read a little bit more about biological evolution, and now it seems that mate selection is also really important. So that's going to be another area of research. But the high level is that the high level is that a self-play environment gives you a perfect curriculum. It gives you an ability to convert compute into data. And if you set it up just right, there is basically no bound to how complex you can be inside the self-play environment. Now, this doesn't mean that it's straightforward to take whatever agents you've trained inside the self-play environment and apply them to something useful externally. That takes additional work. But when you can do that, then that's when you've closed the loop. And then things are going quite well. So I will now have one last topic to cover, and that will be it. Alignment of AI systems by learning from human feedback. And here, the question that we are trying to address is really simple. As we train progressively more powerful AI systems, it will be important to communicate to them goals of greater subtlety and intricacy. And how can we do that? Well, in this work, we investigate one approach, which is have humans judge the behavior of an algorithm and be really efficient. So here we have a video where you have human judges provide one bit of information at a time, where they tell the agent which behavior is more desirable. And so they do it for a while, and after 500 such interactions, you will soon see something amazing happening. It learns to backflip. So you've been able to specify a backflip using 500 bits of information, which is pretty good. How does it happen? This is basically, this is 10% of model-based RL. In a sense, this is model-based RL when you're modeling the reward, but not the environment. So the way it really works is that the human judges provide feedback to the system. They say, hey, this was good, this was bad. All those bits of feedback are being cached into a model of a reward using a triplet loss. You try to come up with a single reward function that respects all the human feedback that was given to it. And then you run your RL on this cost function. And that works pretty well. So this took 500 bits of interaction, and you can train basically most Atari games using thousands of bits of interaction, a couple thousand, something like that. So you can also communicate non-standard goals to it. So in this game, this is a racing game, but we've asked the human judges to communicate the goal that the white car, the one that's driving, should be behind the red car. It shouldn't overtake it. And that's what it learned to do. So that's pretty cool. And what's going to happen in the future, most likely, as these systems get more powerful, is that as we do our work, we will hopefully solve the technical problem of communicating whatever goals we want to these systems. And it is the choice of the goals that will be a hard political problem that we will all, I guess, enjoy or not so much to face. Anyway, that's all I have to say. Thanks so much for your attention.
Thank you, Ilya, for those wonderful videos and the great talk. We have time for a couple of questions.
Thanks for the session, Ilya. So this question is more on the type of research that happens at OpenAI. So I'm just curious, how much role does the philosophy of mind or consciousness and game theory play in day-to-day research at OpenAI?
Well, it's not an easy question,
Yeah,
consciousness.
I know, yeah.
So the real answer is not too much. We don't address or are inspired by this question.
Okay, yeah, thanks.
Okay, I have a question for the self-play. So you were asking how one might want to use that in real life, and you might first say, well, let's just Ubercars place against pedestrian and maybe it learns something. But it might do something which I'm worried in general about self-play. It might sort of end up in a very strange Nash equilibrium where you don't want it to end up, right? You get really sort of sophisticated in some strange corner of the universe where you don't want to be, and maybe you learn all pedestrians jump higher and higher and the cars drive under them, and then in the real world it will not work that well.
Yeah, I mean, I think, so the way I really understand your question is, how do you exercise control on the product of self-play? And the real answer is a big research problem. There are some ideas where, in effect, you will be, well, one naive approach would be you would modify the various dimensions of the environment and see how these dimensions affect the learned equilibrium. You can also set things up so that there will not be an equilibrium, just like in nature. So as far as I can tell, in biological evolution, there is no equilibrium. It just always keeps going. And so, well, I mean, we have different species, and each species is going in a different direction. But it's unquestionable that we will have quite a bit of ability to influence the direction of self-play, but the specifics of it will need to be worked out. Okay, no more questions. Thanks so much.
Thank you, Ilya.